Okay, let's solve the dE now. dy plus y dx equals 2xy squared e to the power of x dx when x equals 0, y equals -2. So we are now looking for a particular solution. So let's try to divide both sides of the equation with dx. So dy dx plus y equals 2xy squared e to the power of x. So y here is our dependent variable, so we are now able to form the Bernoulli dE dy dx plus p of x times y equals q of x times y raised to the power of n. So we can see here that our p of x is equal to 1 and our q of x is equal to 2x e to the power of x. As we can see here, dy dx plus, since we only have y here, meaning p of x is equal to 1, and then this is 2x e to the power of x times y squared. So our p of x is 2x e to the power of x, and that n is equal to 2. Therefore, 1 minus n is equal to -1. So using that, we can now solve for our integrating factor. It's equal to e to the integral of 1 minus n p of x dx, or that would be e to the integral 1 minus n is negative, p of x is just 1, so dx. Therefore, the integrating factor is equal to e to the negative x. And so finding the solution, we start with the dependent variable y raised to the power of 1 minus n, which is -1. Multiply it to the integrating factor -x equals, starting with 1 minus n, which is -1, integral of the integrating factor e to the -x, multiply it to q of x, which is 2x e to the power of x dx plus c. Okay, so this is now 1 over y e to the power of x equals negative integral of 2x dx. So the exponents of e cancels out, plus c. So that would be negative x squared plus c. Okay, that's 1 over y e to the power of x. This is we're looking for the particular solution when x equals 0, y equals -2 from our given. Let's check that again. Okay, x equals 0, y equals -2. Let us substitute these values to our general solution. So 1 over -2 e to the power of 0 equals -0 squared plus c. So therefore, c is equal to -1/2. So substituting to our general solution, we have 1 over y e to the power of x equals -x squared minus 1/2. Let's just multiply both sides of the equation with 2y e to the power of x. So 2 equals e to the power of xy times -x squared minus 1. Or we can factor out the negative sign there, and then let us change this to x squared plus 1. And so that is our general solution, making all positive. So we can write that as e to the power of xy times x squared plus 1 plus 2 equals 0. So that is our general solution. Particular solution. Okay, let's have another one. Fourth example, let's try to solve. Okay, let's try to solve z. 3z minus 5x dx plus 2x squared dz equals 0. So as you can see here, we have z and x, not x and y anymore. But since the coefficient of dz here is more simple, so we're going to divide both sides of the equation. Okay, divide both sides starting with 2x squared and then the other differential dx. So dividing both sides with that, we have z, 3z minus 5x divided by 2x squared, because the x cancels out, plus dz dx equals 0. So dz dx, let's try this, plus 3z squared over 2x squared minus 5z over 2x equals 0. So since this is z and x here, so the form should be dz dx plus p of x times z equals q of x times z raised to the power of n. So this should be the term remaining on the left side, and we are going to transfer this to the right side. Okay, so doing that, to form the pattern, dz dx minus 5 over 2x times z equals negative 3 over 2x squared times z squared. So we can see here that this is our p of x. This is our q of x. And n is equal to 2, therefore 1 minus n is equal to negative 1. So our integrating factor is equal to e to the integral of 1 minus n, so that's negative. You can put that outside. Let's put it outside. Negative of negative 5 over 2x dx. So e to the integral of 5 over 2x dx. So that would now be e to the 5 halves ln of x. Therefore, the integrating factor is equal to x to the power of 5 halves. So now that we have the integrating factor, we can now solve for the solution of the dE, starting with the dependent variable z. So z raised to the power of 1 minus n, which is negative 1. Multiply it to the integrating factor x to the power of 5 halves equals 1 minus n, which is negative 1. Integral of the integrating factor x to the power of 5 halves. Multiply it to q of x, which is negative 3 over 2x squared dx plus c. So this is now x to the power of 5 halves divided by z equals, since both here we have a negative and negative, so that would now be positive. Okay, so we put the constants outside, 3/2, and then we simplify x. So that's x 5/2 minus 2, subtract the exponents, so that's x raised to the power of 1/2 dx plus c. Integrating, that's 3/2, that's x to the power of 3/2 divided by 3/2 plus c. So therefore, we have x raised to the power of 5/2 divided by z equals x raised to the power of 3/2 plus c. Okay, so multiplying both sides by z, that's x raised to the power of 5/2 equals z x raised to the power of 3/2 plus cz. And then we can transfer x to the power of 3/2 on the other side, factoring out x to the power of 3/2. So x to the power of 3/2 times 5/2 minus 3/2 is equal to x, okay, minus z equals cz. So that is our general solution. Okay, and then we have last example number 5. We now want to solve the DE 2xy dy dx equals 2x squared divided by the square root of 4 minus x squared plus y squared if y of 2 is equal to 0. Since we're given dy dx already, let us just divide both sides of the equation by 2xy. So dy dx is equal to, since we divide by 2xy here, x is cancelled and 2x rather is cancelled. So what is left is x over y square root of 4 minus x squared. And then plus, we are able to cancel out y. So we have y in the numerator over 2x. So to be able to form the pattern, we are now going to transfer this term to the left side of the equation. So dy dx minus 1 over 2x times y equals x over the square root of 4 minus x squared y raised to the power of negative 1. So our p of x is this one. That's our p of x. And then this is our q of x. And n here is negative 1. Therefore, 1 minus n is equal to 2. Okay, so that the integrating factor, solving for the integrating factor, is equal to e to the power of 1 minus n integral of negative 1 over 2x dx. So 2 is cancelled. We only have negative 1 over x. So that's e to the negative ln of x. Therefore, the integrating factor is 1 over x. And then we can now solve for the general solution, starting with the dependent variable y raised to the power of 1 minus n multiplied to the integrating factor 1 over x equals 1 minus n, which is 2. Integral of the integrating factor 1 over x, multiply it to q over x, which is x divided by the square root of 4 minus x squared dx plus c. So we can cancel out x here. So y squared divided by x equals 2. integral of dx over the square root of 4 minus x squared plus c. So that's already integrable. This is 2 arc sine of x over 2 plus c. That's equal to y squared over x. Again, we're looking for the particular solution. So at y of 2 equals 0, meaning when x is 2, y is equal to 0, we're going to substitute that. So 0 squared divided by 2 equals to arc sine of 2 over 2 plus c. So on the left side, we have 0 equals 2 arc sine of 1 plus c, and arc sine of 1 is so c is equal to negative 2 times pi over 2. Arc sine of 1 is pi over 2. So therefore, the value of c is negative pi. So substituting to our general solution, we have y squared over x equals 2 arc sine of x over 2 minus pi. So we can just multiply both sides by x. Therefore, y squared is equal to x times 2 arc sine of x over 2 minus pi. That is our particular solution.